All right, I stole this section. This is not in the book at all. I stole it, a combination of one of my, he's a PhD student now, Andrew Wang, but when he did his master's, he did this area and Wikipedia, basically, are the two places. I read a book, you know, beginning near field communication, but it was way too simple. Okay, so I didn't really have anything. Okay, so once again, we're just foraging through the plethora of things that that might exist in the ether of the Internet of Things. Okay, and so we're not going to spend a lot of time on RFID tags because I don't think they qualify according to the definition of an Internet of Things because basically there's not much intelligence in the edge. Okay, uh, so it fits in this same genre because the same technologies that implement um, near field communication will also implement RFID tagging, um, and so uh, and then we can start there because uh, this um, these examples basically have coils in them, and so we'll talk about the fundamentals of the coils, but we won't really do much about RFID at all. It's a passive, and most in which case the reader is the active part. It sends radios back, powers it up a little bit, and responds with a number. So it's not too. Let's see. So there is basically a reflected or a retransmitted wave. Um, so there are active RFIDs, okay, and so a passive RFID is one with uh, no power in the in the in the in the tag, um, and so if you do put power in the tag, then you can increase the distance. Um, but we're gonna, so again, if you think about the reader, which is reading, and the tag, which is writing or saying, so the reader is the listener, the tag is the talker. You could put power in either or both. Well, you have to put power in one of them. Okay, but we're going to focus most of our talk on. Come on, draw on the screen. Oh, guess apparently I can't draw on the screen. On the near field communication, which is a two-way communication and can be used to deliver power. Okay, then now we're going to talk about that. Lots of bands out there for this type of thing. Pretty sure the one we're going to end up with is in the high frequency band. Can I still on this one? I can't. Why can't I draw? Okay, is the high frequency band, the 13.56 megahertz. As you know, whenever you choose a frequency, that implies a wavelength. The and which will imply uh, how things transfer through objects, how far it goes, etc. Okay. So we're going to the examples that we'll get to at the end of the slides are in that 13.56 megahertz range. But as you can see, there are lots of protocols out there with lots of frequencies, and they have the and fairly low bandwidth. This is a fairly low bandwidth type of communication. All right, so let's begin with the coil. Whenever you see one of these things, there's always some sort of twirly thing. The most of the images here were were downloaded from Google Images. but there's a coil. The one in the lower left, got no pointer. The one in the lower left is one of the coils that we built in one of our attempts of creating an embedded medical device. What matters, and we'll talk about what matters, is but the area and the width and the number of coils matter. And you can see sometimes there's 2, sometimes there's 3, sometimes there's 4, sometimes there's 5 turns. Okay. So if we were to look at some of the physics of a coil, right, so this is the receiving coil, if you'd like. And so if you look at the receiving coil, you have a couple of parameters. A is the surface area, right? A is this surface area inside the coil. N is the number of turns of the coil, and dP, dB, dt, okay, is the flux change of the magnetic field. Okay, so the magnetic field is varying in time, and that will induce a voltage on the coil. And so you're going to see an AC magnetic field producing an AC voltage on the coil. That's Faraday's law. Well, in order to make this bad boy work, we're going to have 2 coils. Okay, one in the reader. Okay, that's the primary or the active coil. That's number 1. And a second coil in the tag or the talker or the embedded device. That's coil number 2. And in order to get signal to go from one to the other, we'll derive the mutual inductance between the 2 coils. Okay. Now, in the context of what we're going to talk about today, these coils are so close to each other in what they call the near field of the wave. They're so close to each other that the wave, the electromagnetic wave has not yet established itself. In other words, it's not far field, it's near field, in which case the presence of the 2 coils in each other's, the existence of the 2 coils in each other's presence are coupled, okay, with this mutual inductance. And so we can derive the voltage on the secondary coil. Again, it's the current in the primary coil, I1, is oscillating, which creates the oscillating magnetic field, B, which produces the voltage output on the secondary coil, okay, according to the mutual inductance, M. And so there are 3 properties that will connect themselves, if you'd like, or establish themselves to create the mutual inductance. The inductance of the 2 coils, L1 and L2, L1 being the primary, L2 being the secondary, and this coupling factor K, which we'll talk about in another slide. But before I go on, just so I'm trying to, there's so much information out there and so many different things. What I want to instill on you is some gut feelings about things, okay? Gut. So I will always ask the question, what's better and what's worse, okay? Let's just look at these parameters one at a time. Do you want M to be large or small? That's a question. I asked a class a question. If this were class, I'd be looking at you in the eye and I'd be walking around looking at your faces, okay? I could be walking in the back of the room and talking, annoying the person who's on, doing their email, okay? So I'm in the back of the room looking at you now.
I am.
You want M large or small?
Large.
Large, okay, because current is, you have a limited amount of current in the reader, and you want voltage in the secondary, okay? So if you want M large, what do you want L to be? Large or small?
Large.
Large, okay.
Large.
What do you want K to be?
Large.
Also large.
So these are all things we want to get bigger. Okay, so I'm just saying. Okay, so we go along here and look at some of these. So if we looked at the inductance of a coil, my experience with these equations is they're bogus. They have nothing to do with what the real inductance is. Okay, some physics guy, lied to us somehow, or I never knew what permittivity was. I can't tell you, but whenever I build coils and actually measure them, I've never really gotten close to proving. Okay, see, I downloaded that from Wikipedia. You can see they spelled length wrong. Crap, my bad. Anyway, but nevertheless, there are some terms that we could modify to make L larger. We can have more turns. But if you look at the relationship between N, the number of turns, and L, what do you see? If you, in the picture, as you try to increase the inductance of a coil, you have more turns. But what happens to the L as you have more turns?
It increase, not even
so,
more than linearly.
Yeah, so N can go up, so N squared goes up, but L goes up as well. Okay. Interestingly enough, you don't stack them like a electromagnet. I don't know if you've ever taken an electromagnet apart, but in that you can coil it on top of each other and try to make L small. That doesn't work. Okay. But A is the area. Now A is the problem with A is one of the A's, the A2, if you'd like, the one in the embedded device. You want that to be very small so you can embed this little module into as small as we can. Okay, so stop share here for a second. This is one of our prototypes, and it's obviously not been built yet, but it's a stack. Oh yeah, you can't see the coil. It's a stack of essentially 3 boards. Okay, one of them it's got the coil. Yeah. One of them's got the coil on it. One of them has the digital logic, and one of them has the power converter, and the other one's just for debugging. And we'll break it apart and stack it, so it'll be a cube. When this is built, it's a cube on top. Yeah, so it's a 3-dimensional printed circuit board when that thing is built. But anyway, it's got a coil. Okay. Yeah. Decided not to ask you any questions on this on the next quiz, but if I were, you could, if you knew what each of the terms were, permittivity, area, length, you could calculate the inductance. All right. Okay, so this is the simple circuit model for 2 coils coupled together. Okay, and so what you want to do is I1 is the primary current. Okay, that you're driving into your coil, your primary coil. So all the ones here are the circuits on the reader, and all the 2s are the parameters on the embedded device. Okay, and so what we're going to do is I is again going to be a sinusoidal current, or V1 is going to be a sinusoidal voltage, and I1 will be the corresponding current of corresponding current generated by that V1, and there'll be capacitors. We will physically add capacitors to this circuit, but the resistor R1 is not actually a physical thing that we added on purpose. R1 is the resulting impedance because there is a wire there. Okay, so because the coil is made out of copper and the copper has a length, there will be an impedance, you know, a DC impedance to that coil. And L is the circuit, which is the equation we just did. That's the inductance of the coil. Okay, and there's an R and an L on both sides. And again, C1 and C2 are physical capacitors that we've added to the circuit to make it work. And then in order to solve the mathematical relationship here with two coils in their near field, right, that are mutually inducting, we'll have a basically a coupling parameter of the mutual inductance. So the current in I1 induces a derivative, right? So S, as you know, is a derivative, right? So if you look at this term right here, S is a derivative term, M is the mutual inductance, and I is the current through the other coil. Okay, so there is a induced voltage due to the derivative of the current in the other coil, and conversely, it's mutual, and so I2 is I2, the current in the secondary is coupled back into the primary with a SMI2. Okay? And if you write this circuit in the Laplace domain, something really cool happens. Okay, I mean, it's graphically jumps out at you as a very cool thing, and it's this back arrow right here in the forward arrow. Okay, they're both cool. The back arrow has what consequence?
Is that negative feedback or?
I know it's negative feedback. Okay, so it's negative feedback, sure enough, because it is got a negative term in it, fair enough. But there's something way more fundamentally awesome about the arrow going from right to left. The reason we're here, the existence of this as a topic in this class, is accentuated by the arrow going from right to left. Okay, imagine a system which had only arrows going from left to right. What would be the use of such a system?
Transformer.
Yeah, it would basically be a transformer, which would allow you to send power from 1 to 2. Okay, you got it? So
But you send stuff from 2 to 1?
You can send stuff from 2 to 1. You know, a behavior in module 2 will affect the signals in module 1. That's the communication channel that's uploading data from the tag to the reader, or from the embedded device to the, yeah, so I should have asked, a similar question. That's neat. What is it? Okay, what I'm trying to say is, what's the arrow in the other direction mean? Let's just agree to not make a mess here. Okay. What does the arrow in the left to right dimension mean? What can I do with that? So the arrow from right to left, I can use to communicate data from the tag back to the reader. What about the arrows from left to right? Still can't write. What does that mean? What does it allow us to do?
Some sort of regulating.
No. Good guess. Okay, in terms of big picture, fundamental idea of the whole class is to do what? Communicate.
Send some
Yeah, I can
information.
send data down from I can send data from left to right, from 1 to 2. Okay? I can also send power from 1 to 2. So the arrows going left to right provide you a communication path, a download link, if you like, and also a power link left to right. Okay, so that's when I see this, picture, all the, all the 313 Laplace stuff goes, I get my jury head. But when I see the arrows, I can now see that I'm able to communicate in both directions and send power down. Okay, that's what I see when I see this. Okay. Okay, I think there's another one that I asked. Yeah, okay. So dwelling down in there, because I'm always, I'm a binary person, right? Things are either good or bad, right? So inductance is good. We got that. The L is good. But what about the R's? Remember where they came from, right? The R is caused by the physical resistance of the coil. And everything I do to make L bigger is going to make R bigger, right? Because if I want a bigger area, that's going to be a bigger resistance because the length of the wire is longer. If I want N bigger, it makes R bigger, okay? The resistance bigger. So anything I do to this model to increase inductance is going to make R bigger. But is that good or bad?
Probably undesirable, right?
Yeah. Why is it undesirable?
It's going to eat a lot of current.
Yeah. So,
Power.
okay, the current doesn't, I1 is the same throughout the entire, in this model here is identical. I2 through R2 and L2 and M, that's all the same. And so but R is going to absorb power, okay? And so the way we're going to, okay, so here's a fundamental thing that you knew from your freshman year in college, okay? If I give you V and say, hey, maximize I, right? Because remember, I is the thing that, right? If you look at the left-hand side, the more I you have, the more signal you have on the left-hand side, okay? On the right-hand side. So the current on the left is induced to create voltage on the right. That's a good thing, okay? And so if I just gave you a black box and said, I give you a constant V, how do you maximize I? What would be your approach?
Lower the resistance.
Not just R1, okay? You don't want to just lower R1. What do you want to lower? Assuming, okay, in here you see Z1 is the impedance of C1, R1, and L1, okay? Just Z1 is the total impedance of this circuit, including, 1 over J omega C plus R omega L, right? So what do I want to reduce in order to increase the current? Okay, do I want to reduce C, R, L, or Z? Okay. Multiple choice. To increase the current, do I want to reduce C, R, L, or Z?
R.
Nope.
Z.
Z. So the equation, okay, I wish I could draw. I don't think I know how to draw on this stupid thing. All right, fine. I'll draw somewhere else. Again, the model here, right, is V. And so I in the complex field is simply V over Z1. So if I want to increase I, I'm going to decrease Z, okay? Which was the, which was the, whatever, this from, they're in series. So the math is fairly easy here. Right. But there is a, which of these terms, do I really, when I get to the circuit, I've already built my coil, okay? I've built my coil and now I'm building my circuit, okay? Which of these are inputs to my design and which of these is a free variable? Which are fixed and which are free, freely changeable in the design? If your lab partner comes out of the bushes and hands you a coil, okay, hands you a coil and say, okay, let's do the best we can. Which of these three is given to you?
L,
Yeah.
L is given, right?
that's the coil, right?
Yep. There's one more that's given to you. That's fixed.
R1 is
R.
also
R1 is. Because you didn't put the R1 in there, okay? Because if you did, don't be an idiot, take it out, okay? Because it doesn't help, okay? But you're given the coil, so you've been given R1 and L1. So where's the free variable here?
C.
C, okay. And okay, share, stop share. Okay. We're getting close enough. Okay. So C is the free variable. This is something you probably already know. What happens as you adjust? How does the behavior of this circuit, what is the relationship between Z and C? What happens? Okay, there are the equations, by the way, down there. Okay. What happens if you choose LC correctly is the impedance goes way down. And so we're going to pick the C's so it's that whatever frequency we're oscillating at, this thing is in its resonance, which means it couples very quickly. And we got two C's. We got the C on the one on the reader, on the generator, and we got C2 on the receiver on the tag. Okay, so we have that free variable, which will basically remove the consequence of the R because they subtract each other. I probably missed a negative sign in my other equation. Right? So the idea, we're going to tune both of these coils to maximize the current. Now we can't make it infinite, but we can get it large. Of course, we have to deliver it. Okay, so we talked about the L's and the resonance. Now we'll talk about the coupling coefficient. And again, we got two coils. A1 and A2 are the areas of the two coils. Now, one of these is going to be large, the other is going to be small. Okay, which is big, A1 or A2? Okay, A2 is going to be small because that's in our embedded device. Okay, so I'm just saying it's a embedded device. And D is the diameter of the wire actually in the coil, and R here in this equation is the distance between the two. Okay, so that's what it means to be in the near field. If R gets very large, then there's no coupling at all. Okay. But again, you're going to want to have, what do you want to do with D? Big or small? K, you want big, right? We did that one already. Well, what do you want the D?
Big.
Smaller.
No, look at it. It's double denominator. The D is only shows up one place, right?
Bigger.
Bigger. Okay, you want, now A is a little complicated because in the bottom you've got a logarithmic, square root logarithmic, and in the top you have, A to the 1.1 power. But you probably can guess that the A's in the numerator dominate the A's in the denominator. So you want A large. Okay. So A large, D large. Okay. R small. Okay. You want them close together. Okay. So this is the thing I got all excited about in a couple of slides ago about the arrow going from right to left. Now we can actually give it a name. Okay. We're going to give it a name called the reflected impedance and call it ZREF, the reflected impedance, which is going to be a function of the impedance on the Z2 impedance. So you see there's a impedance in R1 that there's an impedance in Z1 or Zn. Okay, I guess they took these equations from different sources. So yeah, Z1 is correct. Z1, no, all these equations are they're consistent. Z1 is the impedance in just the RLC of the coil, but Zn is the total impedance, including the back impedance of the device. Okay. And so there are lots of schemes in here to communicate from left to right. Okay. I'm sorry, from right to left to upload data. But what would happen if I could modify C2 just a little bit? Okay. So if you go back to Z2 is a function of C2. Right? If I could, and R2 and L2 are fixed, we can't change them. But if I were to modify C2, what would happen? If I could do something on the tag or on the embedded device that changed C2 a little bit, that would have not so much that it's out of tune, but enough to cause a signal on Z reference. So if I oscillated, and I'm going to do it at 10 hertz, by the way, I'm going to take a circuit and oscillate C2 between C2A and C2B at 10 hertz. Okay, go back to over here. Okay. Okay, so let's say okay. So this is the good one. But I'm going to modify the capacitor in the capacitance, because that's a free variable, right? C2 is a free variable. I'm going to modify the capacitance in the receiver as a function of time. What's going to happen to Z reference, the reach Z reflected? Z, not one, not Z. It's going to toggle. It's inverse, but nevertheless, right? So it's going to toggle. So if V1 is fixed, what's going to change?
V2.
No, well, V2 will change, but that's not interesting. Interesting is the uplink. I'm trying to generate an uplink channel. If V1 is a constant and I toggle C2, what parameter here is going to toggle? Yes, I2 will toggle and V2 will toggle. Yes. But one more is going to toggle. Right? Look at. See. Okay. See? If I can toggle this guy, if I can toggle this guy, it toggles that guy. And depending upon how I built the circuit, either I have a constant current source, in which case V1 toggles, or I have a constant voltage, in which case I1 toggles. So either I1 or V1 is going to toggle depending upon the impedance of V1, output impedance of V1. So I'm basically sending data from right to left just by toggling that capacitor. Yeah, it's called impedance modulation, by the way. It's got a name. So I violated, okay, what is the fundamental rule of the entire semester? If you were to take everything I've said in the entire semester into a single sentence.
Encode information as energy.
Okay, I'll take that one. Yeah, sure, you get that one. Bing. All right, fine. So plenty of energy here, right? Because I'm sending, I've got voltage and current here. Yeah, points for that. That's not what it. So I've said many things, and they're all not. I've said they were most important, but I've said it like 10 times. What else have I said is the most important thing to get out of this class?
Read the data sheet.
10-4 points, not the one I'm after. Let me give you a hint. What was absolutely every lab? What was the mantra, the process, the workflow of every lab?
Never write your own source code. Get a reference design.
Okay, not just never write your own source code. Never do anything else. What else do you never do?
Design your own circuit.
Yeah, you don't ever design your own circuit. Okay, and you never write your own source code. Okay, you go out there and you buy what you need. Now, of course, some of you are going to go work at Silicon Labs and whatever and have to make the source code for the rest of us. But the rest of us aren't going to. And so here I violated. This is a classic failure of that mantra. And so this was about 8 years ago, 2012. And I'll show you how it was a failure. But we, not listening to our own advice, decided to build one of these. And so we tried a couple of things. Okay, what's here is the reader coil. Okay, wasn't one coil but two coils, because I mentioned this way back on the first slide, by the way, and that is an embedded medical device for heart function. So we're going to measure the pressure, the volume, pressure volume loops of the left ventricle as the mouse is given cancer and then given drugs to cure the cancer. Okay, or is given diabetes and then given drugs to cure the diabetes, or given heart disease and then given drugs to cure the heart disease. Okay, so that's a typical drug testing process. And everybody wants to know is, does the drug that's trying to treat the kidney, the liver, or whatever, actually have a negative or a positive effect on cardiac function? Okay, so they make a big pile of rats. It could be thousands of them at the same time. And you want to measure things as they both give the rats the disease and then try to treat them. Okay. And so the rats are in a cage. Okay, it's the bottom line of the story. And so in order to make a large coil, we had a large area. And so, why not make the coil the size of the cage? Why not? Bigger coils sound good. And then we dealt with the near field and the far field. I don't know if you remember that. You want the sensor, in our case the rat, to be close to the coil, and in order to make a more uniform field, because the rat's moving around, and you don't want the signal to drop out if the rat is facing the wrong direction. So we can put two coils, and that's called a Helmholtz coil. So we're actually going to drive both coils. Okay, both the top and the bottom. And there's a cool picture. Okay, so do you remember I said that the equations for the the R and the L of a coil are not theoretically relevant. Dr. Pierce has an impedance analyzer. And so when we build our coils, we took them out the pickle and we measured impedance, the real and imaginary parts of impedance as a function of frequency. Okay. Okay. So coils resonate, I guess, as you probably already know that. So there will be an impedance. There will be a frequency at which the coil will resonate. So this was a 6.78 megahertz solution, not 13 megahertz like for the other one, but we're at 6 megahertz. And so, like I said, the Helmholtz coil had the advantage of making a more uniform electric field. Of course, it's an oscillating electric field because that's how it works. So rather than a single coil in the reader, it's a double coil. Okay. Okay, so this was our Envision. It's pretty typical. We got the reader or the base station, which is driving both sides of the Helmholtz coil, the primary coil, and then the rat is the implant, and it's going to collect power, no battery, and then use. Well, I'll show you. It's going to use one modulation scheme to download data and another to upload data. And it's got a microcontroller in it. So the first thing we had to do is get power into device. And so if you okay, so now this is C2, if you like, from the previous. This is the receiver coil. And V sub T is the output voltage of the receiver coil. Okay. And C1's not the same C1, right? So there's already a C in there, right? There's this C2 that's already there. Now we're building past the plus sign. Okay, we're building a load. We're loading down that signal with these circuits. Okay. Okay, so we have a series. A storage element C2 and a diode D1, and that basically raises it up. Okay, so it basically will now float up. Okay, and won't be negative anymore. Interesting about this is, do any of these dissipate power? In other words, if you looked at the energy or power in this circuit, are we losing any energy to heat?
Like ideally, or
Ideally, yeah. No, there's no resistors here yet. Okay. The diode acts as a switch. It doesn't dissipate power. Okay. So floats up. Okay. We haven't lost any power yet. This has got a name. It's Krakoff-Walton voltage multiplier. This is a half stage. It's not very good. We had a full stage. And basically 2 capacitors, 2 diodes. And now, you know, the voltage gets large. We've doubled the voltage, okay, at, you know, at the output, okay, relative to ground. But I said, does it dissipate any power? The answer is no. But if I said the other question, does it generate any power? Is there any power generating other than V, which is the source? That's the secondary coil. Other than V, is there anything in here that generates power? No. Okay. So if I double the voltage, what is the cost of doubling the voltage?
Having current.
I'm having the current. So whatever current is available to run my load, okay, is gone. Okay. So if 1 works, how about 2? Okay. Yeah, sure, that works too. So you can stack these. These are full stage, 2 full stage Krakoff-Walton voltage multipliers. Okay. And so because you got to get up over 1.5 volts in order to run the microcontroller. Okay, that's our scheme here. In order to get the microcontroller to reset, to run, we need a voltage over 1.5 volts. So we'll use enough of these stages to boost the voltage. Okay, then obviously it has a regulator and, you know, that kind of stuff. And so there isn't anything fancy about the download modulation. It's, in other words, sending data from the reader, from the base station down to the implant was amplitude modulated. So it just oscillated at a different amplitude. And they're obviously relative to each other. And so it can pick up, the receiver can pick up changes in amplitude, because I just have to measure that. I basically have to measure the voltage prior to the regulator. Okay, so back over here, once I've regulated it, if I connect the regulated power line into an A to D converter, I can see the amplitude modulation. And this is kind of, this is the output, the AM modulated output. We cranked up the power to make this thing work, and I ended up at 100 volts. Okay. Let me decline that. Okay. Obviously, that's the reason you don't build your own circuits, because you make stupid mistakes. We clearly did something completely wrong to have to run at 100 volts. But we made it run. And the difference between the blue and the red is the AM modulation. That's the ones and zeros that it's sending out. So it's a small difference, but it's still measurable on the receiver because it's linear, right? So whatever, a 2% oscillation on the power line is going to show up as a 2% oscillation on the other side.
what did you use to generate this?
Oh, I didn't show you the circuit. I mean, it was okay. We started with, okay, so how do you make us, all right, so how do you make a sine wave? Yeah, that's a good answer. How do you make a sine wave?
A DAC?
Okay, that's one way to do it.
Spin
You
something.
gotta make it at 6 megahertz, right? So if you go your 319K route, you got a very fast DAC to make sine wave at 6 megahertz. All right, so how about I'll do an easy one? How do you make a 6 megahertz square wave?
Crystal oscillator.
Yeah, a crystal oscillator. And how do you make a square wave into a sine wave? Well, with a
Filter.
Remove the,
okay. So how do you make a okay? Okay, it's not this circuit. This well, yeah, that'll work. Okay, so if V1 were a beautiful sine wave, how do you make it a large current sine wave, a voltage? How do you drive lots of current at that same shape? What kind of circuit takes a regular old voltage and then creates a better voltage with more current?
And off amp.
Yeah, but not a power amplifier. Okay. So do you remember the days when you did they ever teach you transistor amplifiers? Try to? Yeah.
Who's they?
411, 430. You probably didn't take 438.
I did not.
Yeah, in 438, they'll teach you how to make a yeah, just Google it, right? So to use a power transistor in linear mode. Okay, so how about this? This you do remember. In 306 and in 319K and in 445L, we said transistors were what? What was the behavior of a transistor? In 306, no, it's not required anymore. No.
Oh my
Not
gosh.
for- yeah, almost nobody takes 430. Yeah, it's 438 is required for a couple of the tech cores, right? For the IC tech core, for the yeah, for boy, which one is it? Which one? It's another one. Yes, things have changed.
Oh, so it was required before.
It used to be. So did 422C used to be required.
Well, that
Oh,
was even before my time. So
Yeah, 422C used to be required. We should make everyone learn Java. It actually used to be C++. Yeah, they reduced the number of requirements to let people specialize more.
That's not where the dinero is at. That's why.
Well, okay. No, it actually has to do with postulate number one. What was the most important thing that was in this whole class? Don't build your own circuits, man. Go out and find it. Put the pieces together. Okay.
But who's gonna make the circuits?
Yeah, but
Someone
somebody
has to.
will. So there is a track for which 438 is a requirement. They take 438, they take 438K, and they take, they do a bunch of power circuits, okay. So getting back to my story is in 319K, we said the transistor was used as a what? In 306, 319K, and 445L, we used the transistor as a what?
switch.
A switch, a voltage controlled or a current controlled switch. Okay. We did in saturated mode. We were either in off mode or saturated mode. Well, it has a linear mode, and you just got to be smart about all the circuits in order to make the output a linear function of the input. Okay. So that's how you build it. You hire somebody who's in 438, taking 438, and they know how to build it. Or you just buy the whole chip integrated. Okay. This is how we did the upload link. We basically had a GPIO port, and we just switched the coil, not the whole coil, just a little bit of coil. We switch a little bit of capacitance into the coil. So basically all we did was, and so our uplink communication was a GPIO pin, which was, again, modulated. Of course, we did it at 10 hertz because we knew nothing. And we basically detuned the coil one way or another, basically setting up the capacitance we added to the secondary coil to be two different values. Yeah, no, Austin, another one. We used to require chemistry. Yeah, it used to require chemistry as well. Yeah, we used to require 325. Well, there was a bunch of stuff we took out. Oh, we used to require 339. We used to, yeah, there used to be a lot of requirements.
Oh, that was the worst class.
Well, okay, it's only worse because it was taught poorly. Okay. Yeah, I'm just saying yeah, let's see another one. Here's another one that you, those of you in the PhD program, how many courses do you have to take?
8.
No, 10. PhD, 10 grad classes.
Okay.
When Pierce and I were graduate advisors for the BME track, we made them take 17. Yeah, just saying. You guys got it easy. No, you don't. Life is way harder than it used to. Life used to be easy. Now it's harder. Okay, let's go back to my thing here. All right. Here's some of our signal. So we were all excited. We got two very exciting moments. One, when we could power the device and we saw the LED flash on the device. And then this one, what's in the lower right is the filtered, demodulated output, because you remember the GPIO pin on the embedded device was oscillating at 10 hertz. And this is the filtered output, scaled, whatever signal on the base station, which showed that same 10 hertz. So we were excited. But, it was all for moot because, right at the same time, or even historically before we even finished, people started making chips to do this. Oh yeah, here we made one. Okay, so I showed you, this little green one was one of them. This one is another one.
Is this active or passive?
Okay, okay. There's a microcontroller in there that's executing code. We can download whatever crap code we want in there, and it can take commands from the base station, perform measurements, and upload results. So it's active. Okay, it's a completely open-ended implementation that could do anything a microcontroller do without the battery. Okay, of course, its communication channel is only 10 hertz. Okay, I'm gonna say this in the next slide up again, but I'll say it here. If there's since it is active and no battery, what has to happen for this thing to be running? Right, it has to have power. Okay.
Is it reading from an active or passive device?
Okay. How are you defining active and passive?
Like, does it require power?
It
Can this
gets
read from a
power
coil?
from that's what whole this crap is for. It gets power from the coil.
But I thought your lab has power to both, right?
No. Oh, no, it doesn't. No, you're talking about,
Yeah. Your
I
lab.
never actually finished the power. Okay. Okay, so where'd I put it? I never, yeah, Austin did one, or somebody did a lab 4 on this, but where'd I put it? Oh yeah, here. Okay. You're getting a little bit ahead of myself, but that's okay. Let me stop sharing for a moment. Okay, so let me, yeah, sure, that'll be fine. All right, so here's one that actually works. Okay. This is an embedded device which has the thing we just showed you. Okay. It has this circuit in it. Okay. But the stupid kids don't know how to, they're computer scientists. They don't know how to mold plastic. So there's no battery in here. Just warning you. Okay. So I don't know whether you call that passive or active. I'm going to call it active because then you take a a coil here. Here's one. Here's another one. This is obsolete. But you take the device and you stick it close to it, and now they're communicating. Now they don't have to touch, but you get them close, and this microcontroller starts running. And again, I can run whatever code I want on there. And so this is a base station. This one here is another base station. Again, it has a coil right here, and you get this device to program there. Okay.
That was the lab you were gonna give us?
Yeah, that's right. But these are the parts. They're sitting here in my lab. I have not put. It's still here. I got it close enough where I could program the registers in here from that.
But I thought this lab you had to power both.
Okay, so if you're a WIMP, this whole field, near field, can be, you can do it with 2 batteries or 1 battery. Okay, this field can work. You can do a two-directional communication channel with 1 battery connected to this guy, powering the transmit coil, and no battery on that one, which gets its battery through the coil and communicates through the coil. And I'm about ready to tell you why 2 batteries is better than 1. And you already know why 1 battery is better than 2 is because it's more mobile, it works forever, okay? But one of the advantages of, RFID, one of the advantages of 2 batteries is there's an A to D converter in there. Okay, I promise you that's how it works. And therefore, if this thing is active, what is the what?
Sorry. Are you screen sharing?
Oh, I'm not. Sorry, I should be. All right, thank you. It looks beautiful to me. Okay, so can you see it now?
Yes.
There's an A to D converter in there, in that chip, right? That big red chip. That's an MSP430 with an A to D converter in there, because I'm going to measure stuff. But while this is powered, I have that high frequency coil activating. Okay? And so what do you suppose happens to the signal to noise ratio of my A to D converter?
It goes down.
It goes way down. Okay, so this, I don't know whether you want to, I'm going to call it active because it's running code and is completely intelligent. Any intelligence you can put in any microcontroller will be intelligent. It's just noisy because the coil's running. Okay? And I wouldn't say it was an epic failure. It was just a fun project. You know, it was clearly we learned a lot about coils and what to do. These little dongle craps is how do I program it? I program it, then I cut that part off. So along the same time, pretty much the same time period, the 2012 to 2013, IC manufacturers started building this for real. And so they integrated all of the analog circuits and all of the modulation into the IC, just like the entire class, right? Whether it be sensors or Wi-Fi or Bluetooth, we're going to integrate as much as we can into a single chip. Okay? There is an A to D converter on this chip, but it's going to be noisy when I'm running batteryless because it only works with the coil active. Okay? So it's basically a coil, that's the L, and a tuning capacitor, that's the C, and the rest of it, it's all integrated. So after this little ISO 693 stage. The rest of this is just a plain old microcontroller. Okay, well, it's a little bit plain old. It's got both FRAM and ROM. ROM is where they put in the libraries for the near field communication 15693. Ferromagnetic RAM is where you put your programs. Okay. Yeah, we tried programming these chips before we soldered them down, but apparently soldering erases the FRAM, and so we had to for this application we also had to build dongles so that after we soldered the chip on, we could program it. Okay, so this is basically just the mantra of the entire semester, and that is, okay, so I'm done. All right, so showed you this. This is like, now we're at 13 megahertz. Yeah, and so that's a development board, and then the big black chip sort of in the middle is the MSP 430 with this radio frequency modification to it. And so you just line up the two coils of this in the sensor coil in order to get it to communicate. Let me show you the encoding. Okay, there's the reader. There's a bunch of different readers. The one in the upper right is the current one. The other two are obsolete, but they got coils in them, and you get the two coils together. So it's like there, because there's two coils together. And so this is the downlink. You see the downlink from reader to card. Okay, from reader base station to implant is pulse position modulation. And you basically you have a fixed time period T, and then you give it a pulse somewhere in that time period, 2 to the M different places in that time period. You give it the pulse, and so that will encode M bits per symbol. Okay, so for instance, 2-bit symbol is you have 4 different places you could put the pulse in every time symbol, and so the symbol time here for 1 out of 4 is 75 microseconds. But you got 2 bits in that 75 microseconds. This is the fast one. And so this has to be closer to run at 26 kilobits per second. If you go 8 bits per symbol, but do it with a longer symbol time, a 5 millisecond symbol time, with 8 bits in it, it's more reliable, but it's slower. Okay, that's 1 out of 256. Now the amplitude shift is not, this is a again, this is you've got the 13 megahertz carrier. Okay, that's always running, but then you add a 400 kilohertz on top of it. So you've got 2 frequencies added together, the power frequency at 13 and a modulating a communication frequency at 400 kilohertz. And then 0 is 8 pulses followed by 8 blanks. A 1 is 8 blanks followed by 8 pulses. And it's got a start frame where 24 pulses. I mean, a long time of no pulse, 24 pulses, like a start bit of a UART. And then the stop bit, if you like, is 24 pulses. So 24 pulses together is either a start bit or a stop bit. Okay. That's called Manchester, by the way, where you send a bit as a 0, 1 or a 1, 0 or nothing, something or something, nothing. Okay, what time is up? Okay. So, again, you know, we're pretty successful in making this work. It's got the problem when it has no battery here, right? This is TI's version. This one was our version down there, the lower left. The problem is the 880 is very noisy. But you know, but you can get it pretty small. That's the whole point here. This is pretty small. And you're really limited by you notice their coil and our coil were different. You see the difference between the coils? This coil and that coil?
Yours has more loops.
Yeah, but it goes, okay, so look at the 880 converter of the two. Right? The 880 converter is not in the coils. Okay. And it's got that weird blue, look at that weird blue trace. You see it? So the EM field has to go through the black, right? Look on the right. The electromagnetic field has to go through the coil for it to work. And so the area of this coil is essentially the surface area of the black. Okay. The blue are small enough that the electromagnetic field doesn't go through. It's like a screen door and the flies can't get through, right? So what can you say about the 880 converter on this one? And all the analog circuits are in there too, by the way. All the analog circuits are in the blue field. And this one, right? This 880, our 880 converter is going to be more noisy than theirs. So the next time I build one of these bad boys, I'm going to look like that. So I'm at the end of my time. We got I had one more lecture ready to go, but I'll just leave it up. So I just wanted you to remember the fundamental rule is go ahead and look for software out there. Go ahead and look for circuits, especially if there's a single chip that can solve your problem. Yeah, let me know if you want to put yourself in the. Now you have the option of taking the quiz on Tuesday and then choosing to do a lab. Okay, that's still an option if it doesn't go well or if you don't feel like studying. So Tuesday's the quiz. Thursday is Yarabali. The following Tuesday is Ben, and then we got 2 days of project demos after Thanksgiving.
Do we have to show up next Tuesday if we're not taking it?
Oh, no, please, no. I mean, anything we announce, I'll put on Canvas. If we announce something that's not quiz related, I'll put a Canvas announcement. Well, we made it. Thanks. I did figure out a way to download the video, so I'll work on. I got my lecture for today done, so now I can do something else. I'll make a YouTube channel. I'll work backwards, and upload the Zoom videos as a YouTube channel. Anything else? Oh, Rita, were you gonna check out?
Yeah, can I still do that?
Yes, you can. I'm gonna stop recording.